Hi everyone, this session covers the topic of orthogonal projections. So what we will do is to go through the definition and consider the general properties. We look at orthogonal projection onto a subspace, and in section 4, we look at associated matrices. If you had the course of first year linear algebra course with me, then the only topic from this session that I didn't actually cover was uh, section 4. Section 5 is concerned with orthogonal projection onto a hyperplane or intersection of a few hyperplanes, and we can derive an easier formula for that. Then finally, I discussed the distance to a subspace, which is the main point of using orthogonal projections for optimization problems. For simplicity, what I will cover today is mostly on Rn, but whatever I say can be extended, generalized to Cn. The only difference is that you should be careful when you're using a standard inner product for Cn. We put conjugation on the first vector. Okay, we can also put the conjugation on the second vector. Only one of them we have to choose, but I'm using physicist notation because that's how I taught this in the class. Okay, but whenever you see in Rn, whenever you see a transpose, an analog in Cn would be the adjoint. So you conjugate and transpose. So let's recall what the definition of an orthogonal projection. So we have a map, P is called, which is linear from Rn to Rn. Of course, this general is much more, can be extended to much more general cases than Rn itself, to any vector space equipped with an inner product, real or complex. Then we call P an orthogonal projection if P squared is equal to P, means that POP is equal to P, and the inner product property holds, okay, for every V and U. So this is not very intuitive. Let me say another intuitive definition about orthogonal projection. So what we want is that the green part, if we have V, and if we want an orthogonal projection, we demand that this green part is orthogonal to the plane. Means that any W that we take in the plane is actually orthogonal to this green bit here. So V minus PV is here. And okay, it can be translated to the origin, but the picture is good enough, I suppose. So this is orthogonal to every element of the subspace W. And that's what we demand for an orthogonal projection. Then you can easily check that the definitions 1 and 2 are equivalent. So some properties that are important to recall is that when you have V for our orthogonal projection, you can write V is equal to image of P, direct sum with kernel of P. And also the orthogonal complement of image of P is actually equal to the kernel. So that implies one very important property of an orthogonal projections. So for example, if we have V in V, we can write V as W1 plus W2, where W1 is in the image of P, and W2 is in the kernel of P. Okay, so P of V, it becomes P of W1 plus 0 because W2 is in kernel. But we can also check for W1 in the image of P, then P of W1 is actually equal to W1. That's because of P is a projection. Okay, so this is equal to W1. And because this decomposition in when you have a direct sum is unique, so we can find W1 and W2 uniquely that their sum is equal to V, means that if we know the image of P, then an orthogonal projection is identified, is uniquely identified. I mean, knowing the image, then we know from this property the kernel of P as well. And because of this property, we can write the decomposition, and this decomposition is unique. Okay. And that decomposition being unique, we can already understand from this decomposition any vector will be mapped to P of V, and that P of V is just equal to W1, which is uniquely found because of this direct sum. Now assume that the Rn with this Sn or linear product, we are given one orthonormal basis for this space, vector space. Then any vector, any v in V is certainly can be written as a linear combination of W1, Wn. So means that there exists mu I in our field, which is R here, then such that V is equal to mu1 V1 W1, sorry, mu n Wn. And if you take the inner product of but V, if we take the inner product with W, Wi, if we take the inner product, Wi kills basically every element here except Wi itself because of this being an orthonormal basis. So this gives us mu I. So that's very nice, means that the coordinates of one vector of a vector space in with respect to an orthonormal basis is very simply identified with some just an inner product. Okay, so that's good. But so that means that if we have one vector, we have an orthonormal basis. To find the coordinates here, we just take the inner product, which each of these orthonormal bases, let's say W1, W2, and W3. And this gives us the coordinates that we are looking for. Okay? And that's it. Now, I consider this subspace to be W. Okay? So, but V was written as the sum of Wi V V W I equal to 1 to n. So if we take actually a chunk of it, only k of these elements here in the sum, k of the summons, then we can just write this Pw of v equal to this sum, okay? And we can easily verify that this is actually an orthogonal projection. And also we can say that image of Pw is actually equal to W, which is the span of W1 to Wk. Okay, so this is the W, and this defines this orthogonal projection. Okay, so, but by remark that we mentioned, remark star, if we have image of P, then P is completely determined. Means that if we have W1 through Wk that are an orthonormal basis for W, then this, as soon as we prove that this is an orthonormal projection, orthogonal projection, meaning that satisfies P squared equal to P, and the second property V, W, and U, let's say, equal to P, V, and Pu for any two vectors of the space, then because the image of Pw here is equal to W, the subspace spanned by W1 to Wk, then Pw is determined, means that Pw, one of the consequences, does not depend on the choice of the orthonormal basis for W. Okay. Now we are at the stage to address the main question of this presentation. We want to find a matrix associated to this linear map PW. Okay, but when we want to find a matrix for a linear map, we should first fix a basis. Okay, so the first question would be, find this matrix associated to PW with respect to W1 through Wn, such that these were actually defining PW, and these are an orthonormal basis. But the second question, which is more interesting for many people, is to find this matrix associated with the standard basis. Okay. Okay, we are given this map PW, and we want to find a matrix. The matrix MBB, recall that it's a matrix that if you multiply it to the coordinates of a vector V in B, in a basis, takes them to the coordinates of the second basis, takes them to the coordinate of PW of V in the second basis, which happens to be the same basis that we are considering now, B again. So let's just write. And how do we find such a matrix? We just write the elements of the first basis and apply W1, PWK, PWN, and we write this coefficients of the linear combination as columns of the matrix MBB. Okay, I have made another video concerning this, so you can just watch that. So if this is equal to something in terms of W1, W2, Wn, then we put these coefficients basically BB of PW will have these things as its first column. So we put the coefficients here. Okay, but it's just easy to see that by definition, this is actually equal to W1, and this is WK, and then the rest is 0. So PK WK plus 1 is 0, and etc. This is also 0. So the coefficients that we get are very easy. Here is 1, here is 0, etc. Recall that if you have a basis and you write one vector as a linear combination, this linear combination is unique. So these coefficients that we are finding are uniquely determined. So this is like that, and then we get basically 0 W1, 1 W2, etc. W. And we continue like that. And if you put them in a matrix, this would be the first column, the second column would be 1, and then the kth column would be give us 0 here, and then 1, and then the rest is 0, 0, and 0. Okay, let me just write it nicely in the form of block matrices. So this is, here we get an identity matrix of size k. Here we get a 0 matrix, and here we get 0, and here we get 0 matrix of n minus k, n minus k. Here we should, so the whole matrix is n by n, and of course we can write this is n minus k times k, and this is k, and this is k times n minus k. Okay, that's very nice and simple, but you might ask, what's this matrix if we want to write it in terms of the standard basis? Okay, and the claim is that if E is a standard basis, just let's recall E is equal to En, and we want to write this. So what do we mean, first of all, by this? So Wi equal to, when I'm writing this, so W, let's say I1, W, In. These are the coordinates of Wi in the standard basis. Okay, and now what do we want? We want M E E of t. So we are looking for this matrix M E E of t. Okay, but we know already what M B B of t is, which was very simple. And if we consider the matrices of change of basis, so let's say CB, so here we have E, and here we have B. So the matrix CBE changes the coordinates of one vector, which is written in terms of E, to the coordinates in terms of B. Okay. Then we have also here CEB. Of course, we have both direction, which is this is equal to CBE inverse. Okay. Now we can just write from the commutative diagram. We start from E, and then we end up in E as well, and this is the case. So if we actually, because we have this matrix, if we calculate CEB and CBE, then we are done. Okay, what's a CEB? It's just we have to write elements of the standard basis B um, in terms of E. As I said in the other video, if you are going from B to E, convert all your B's to E money. Okay, and so this is, we want to write elements of B, which are W, etc., in terms of W. Okay, but these coefficients, when the vectors are given in Rn, when there is where the no basis is specified, these coordinates themselves are given in standard basis, and that's the assumption here. Okay, so what coefficients we get here, we have to put them in the first column of this matrix CEB. Okay, so CEB would be basically this matrix whose first column is W1. Its second column would be W2 through WN. Okay, now we have another thing also. So CBE is equal to CEB inverse, and but because W1 through WN is an orthonormal basis, this matrix CBE is unitary, or in the real cases they're actually called orthogonal, but that doesn't matter, means that CBEB CEB transpose is identity. Therefore, CBEEB, is equal to the inverse C. Nice. So we can easily find, and this is equal to CB. So to find the matrix CBE, we just transpose CEB. Okay, that's very nice. So we have to calculate this thing. So this is equal to CEB. CEB is the matrix of W1, Wn. We know this matrix, which is 1, 1, 1 till k and 0, all 0 here, and W1, Wn transpose. Okay, but that's not what we wanted to prove. We wanted to further simplify, and we can easily, so this is a little exercise to check that this is actually QT. Okay, so let's say check. Okay, remember that the Q is not even a square matrix, okay? But if when you multiply this to this matrix here, a lot of information from will be lost. So basically, we don't. It's not necessary to know WK plus 1 through WN, okay? And that's actually what it implies. So this is very nice, and we so see that. And also, it's important to say that QTQ, which is a K by K matrix, is actually equal to the identity of size K. So now we have a question. If W is equal to span of V1 through Vk, and not necessarily an O and B orthonormal basis, how do we find the matrix MEE of PW? Now what we found, QQT, was in terms of an orthonormal basis. But so the question is asking, how can we further simplify this? One answer is that just, well, it's not probably the best answer. Weigrammer-Schmidt to an orthonormal basis, then from this orthonormal basis, we have everything. But the answer two, which is very smart, is saying that precisely this matrix can be found using this matrix A, okay, whose column are V1 through Vk, and calculate this thing here. Okay, A transpose A, inverse AT. Okay, that's very nice. But just let's emphasize that this is an n times k matrix. So it's not a square matrix. We cannot talk about the inverse of this matrix per se. So just don't confuse, don't write A star or AT. A inverse equal to A inverse AT. This doesn't make sense at all because this is not defined. Okay, it's not a square matrix. Good. So what's the plan? The plan is to write QQT in terms of V K, in terms of A, this matrix, and let's see what happens. If we write, because V1 is, because it spans V1 through Vk span W, so V1 is of course in W. V1 can be written as some linear combination of elements of W1 through Wk, because W1 through Wk also span this subspace. So let's put this here. So let's put some coefficients R11, K1, okay, RK1, WK, okay. And so we can write this for V1 through Vk, but what happens is that V1 is written now equal to W1, WK, this is our matrix Q, and R1, 1, RK1. Okay, that's very nice. If we actually do this for other vectors, Vk, then we will get R1k, W1, RKK, WK, and then we put them in the last column. Okay, so this is R1k, RKK. So this is a K by K matrix, okay? And we want to say that, first of all, this is an invertible matrix. Let's also denote this by R. R is invertible, and it's not hard to verify that. So now we have A equal to QR, okay, because of this, and check that R is invertible. Now we have and the matrix we were looking for, PW, is given by QQT, but we want to write it in terms of A. So because of that relation, we have A R inverse equal to Q, and then, so let's just, it would be A R inverse. So this is A R inverse, and R inverse transpose A T. So this is equal to A R T R inverse A. A nice little trick here is to write this RT R inverse AT. Recall that Q TQ is equal to the identity of size K. So we can just insert it here. You can check that actually the sizes of these matrices make sense to actually do that, to multiply to K by K matrix here. So here I'm just inserting QTQ, okay? And now we're done because this is A, this is AT indeed, and this is A indeed, and we have the inverse and 8. Okay, that's very nice. And we have that. Let me say a few words about an orthogonal projection onto a hyperplane. Hyperplane means a plane or subspace which is given only with one linear equation. So the linear equation, it can be written as this inner product. It's equal to 0. And, well, if you have W equal to the set, then of course, if we find one orthonormal basis for W, then it is easy to write PW of V. But in general, it might take actually, well, there is a much easier way to do this. And just observe that the W is actually this vector B orthogonal complement. Okay? And therefore, B is actually perpendicular to all of W1 through Wn minus 1. So what we get here is if we put B naught equal to B over the norm of V, then W1 Wn minus 1 B naught forms an orthonormal basis for the whole space. Okay. Okay, that's very nice. And what can we say? We can say that V is equal to W1 V W1 Wn minus 1 plus W. Okay, let me make some space here. And then we can write this is equal to B and V, B naught. Okay? And therefore, this part is P, W, V. And what can we say? Therefore, P, W, V can be easily written as B naught V. Okay. So, or we can write if this is the projection onto the span of B naught. So let's say PW is actually equal to identity minus the orthogonal projection onto the span of B naught. Okay, and that's it. So this acts on, if we look at the action on V on both sides, we actually get this equation. Okay, very nice. We can also write the matrix would be, of course, identity minus the identity matrix, which is n by n, minus a span of B. Okay, projection onto the span of B naught is the matrix we found is B, BT, B naught, or the other formula that we can't calculate it without assuming that these are this is normal, would be B times this number, which is B T B inverse B. Okay, B naught is a normalized B. So, and then we have that. So this is equal to, of course, in minus BBT divided by norm of B squared. Okay, that's very good. We have one other problem that I wanted to mention is that assume that W is given as an intersection of some hyperplanes. So for each I, okay, and so then we can just write the associated matrix to P. Okay, this is not accurate, so I have to write this. Okay, so this here we need, of course, to be have rank K, so that it's a K by K matrix to have to be, for that to be invertible, it must have rank K. That means that B has to have at least a rank K, and that means that B1 to BK have to be linearly independent. Okay, that's good. In many applications, we need to find the distance of a point to a subspace. Means that, for example, if we are given 2 points in our space, V and W, of course, the distance is defined as the norm of the difference. But if we are given 1 point and one closed subset actually, We define the distance of V and W equal to the minimum distance of V and all the points in W. For example, if V is here and then if you have this complicated W, then the minimal distance, so you find basically this point in W, W naught, let's say, that has the minimal distance to V. When we are working with subspaces, we are in luck because to find, um, so let's say W naught such that the distance of V minus W naught is less than or equal to V minus W for all W in W is just given by PW of V. Okay, so means that orthogonal projection of a point to a subspace gives us the minimal distance. So, and why is that? Because this triangle over here is a right triangle and it satisfies Pythagoras theorem. So the red one here is actually V minus W, and here is V minus PWV. And because this green part here has non-negative non-negative length, then we have the inequality. Okay, that's very nice. And therefore, what we can do is to use the orthogonal projection and all the formulas that we have found to say that the distance of one point and subspace is just given by V minus PW. Okay, that's all I wanted to say in the session. Thanks for your attention.